give it a few more minutes as usual for people to come in. But in the meantime, homework one is out. I see that some of you have started it. I also saw that some of you have trouble setting up the environment and just working with Jupyter, whatnot. Um, is there any other pain point, like, or anything that would help? Yes. Mm. Yeah, okay. Um, So for Grayscale, I wouldn't be able to ask any more if I give you the output. But so the Jupyter notebook has a bunch of sample values in it for, say, rotation and scaling, like rotate by 45, I think is what's in it by default. So I can include output. Yeah, yeah. So for grayscale and inversion, since it's just a single operation, there's nothing different that I can ask you to do. What I was saying is that the default values, if they're 45 for rotation, then you should pick a different value once you know that your code's working. And I'll give you output for one value. Okay.
For the coding part, we don't have to submit on UB Learn, right? We just have to
No,
commit to
yeah,
GitHub for after every task.
yes,
And only for the written part, we have to submit as PDF in the UB.
correct. Um, for the code part, would it help if you had resources to refer to for how to use NumPy? Just show of hands if anyone's having trouble with the indexing, slicing, adding, uh, stuff like that. Okay. Um, Environment setup. Uh, I'll be able to record a walkthrough of how to do that for Ubuntu. Um, Windows, I was planning I'll go over it at the end of class today, if that's okay with everyone. I guess if you don't need to know how to do it on Windows, you can leave early once I get to that part. Whoever wants to see can stay. Um, I'll do it on my laptop. Um, and Ubuntu, I'll record it. Uh, I don't have access to a Mac, so OS X, it's going to be pretty similar to how you do it on Ubuntu with just a couple of minor differences on um, where to get certain things. Uh, OS X, typically you would use a package manager like Homebrew to install the GitHub CLI or Conda or whatever. Um, I can write up more detailed instructions with screenshots for that. Um, okay, probably on time, 10:34. All right. So today we're gonna start getting to some of the actual fun stuff. I know I've said that before when we were talking about edges, and edges were relatively fun compared to what we were talking about before that. But now we're getting to actual applications. Um, all of us have smartphones, right? Um, we I don't know how you guys felt the first time you tried taking a panorama image and point your camera at something, go in a bit of an arc, and then it stitches all of them together. That for me was pretty incredible. That was something that I could just have in the palm of my hand. This is when probably about a decade ago when I got my first smartphone. Um, So we see that these two images are similar, right? If you spend a few more seconds on it, we can also tell that there's some overlap somewhere. Uh, how would we go about stitching a panorama? So just purely from intuition, you just have two images and you want to line them up together. What would you look for? Just throw words out. Correlation is good, yes. Yes, just not even in terms of anything that we've done so far. Just you have two pictures and you want to try to line them up where they overlap. What do you look for in the image? You don't know what pixel values are. I'm giving you two like printed pictures, and they have some overlap. So louder, can't hear you. Stick them. Uh, how would you know where the right place to stick them is? Yeah, okay, okay. So edges, sure, not in context of like arrays of numbers, but when you're looking at an image, you'll try to find just something that's similar between the two, right? You find something that stands out from the rest of the image and that you can use to sort of locate something of interest within the two images, and then you try to line them up. So regions of interest that we can use to do things would have to be regions that have uniqueness. And that is something that we also need to be able to represent mathematically since we're trying to do everything with code. Because if it's a panorama, sure, you could take a video of the whole thing, but we want a still image that is a composite of a bunch of separate images. So the regions of interest that we care about that are unique are what we would call features. And we're going to be dealing with this a lot the rest of the semester. So what's important is that they need to describe something about a region, and we can then build on features once we have located them in the image to either stitch a panorama, search for objects, um, see if there's correspondence between images, estimate projections, so that you can reproject another. So the example of the panorama, this is, you're taking a picture, looking at something, and then you're taking another picture. So there's not a lot of change in perspective between the two images. But if instead of moving the camera in a wide arc, I I personally took a step aside and got a different view. There would still be overlap, but there's an angle between the two frames that were captured. So we need to be able to account for that also. So first step in our panorama stitching pipeline is identifying features. Um, Cross correlation, someone touched upon this when I initially asked how we would find which regions are similar. Um, it can be done the way we did it for template matching. You would have to divide the image into a whole bunch of small patches and then do that for every other patch. So that's, if you think of the complexity of that, it is the square of the number of patches you have. So that's not good. We need something a bit simpler. So assuming we have a region that we care about, we can take that particular patch and the other patch that we think is similar, the one that we want to check, and then we just subtract one from the other directly, which gives us the absolute difference between those two patches. Um, and if you don't want to deal with the sign, as in which of those has the higher or lower values, then you just square the entire matrix once you get the difference, and that is the squared error. So we're looking for regions that are unique. Um, we we know how to compare patches if we assume them to be similar, but to have candidate patches to compare, we need a way to identify regions that have a degree of uniqueness. Say I pick this one patch from the sky. If you zoom into that part and just look at the pixel values, it's mostly just blues there. There's not much variation. I could, if you gave me just this patch and told me to pick out where in the sky it is just by looking at it, I couldn't do it. It could be anywhere in the sky because there's um, barely any variation within the patch, and it's easy to confuse with other parts of the sky. Another candidate patch is one that would contain an edge like that over there. If you're sliding it vertically, so now that narrows it down a little bit. If someone gives you just that particular patch, then you can guess that it's probably somewhere along that edge, but um, exactly where along the edge, hard to say. Any guesses on what a better feature would be, or a better candidate region would be? Yeah, corner. Um, so if you pick a corner, it's what we would also do naturally, right? If you're trying to match up two images, see where they are. That's I know that's where I would start those little peaks. On the left image, this part right here. Um, right image, this part right here. Those have corners. So the good thing about it is whether you move it vertically or horizontally, there's really only one place that you would be able to find that exact patch. Now, we have a candidate patch um, comparing similarity, doing correlation for all of them is computationally intensive, calculating the distance. So I mentioned the absolute error and the squared error. You could do that for this patch versus every other patch in the image. But again, that's a lot of computations that we'll be doing if we're comparing it with the rest of the image. So instead of that, what we do is we just shift each patch, each candidate patch that we have by a tiny bit, and subtract it from itself. Um, so if you have uh, a patch of the sky and you subtract another patch of the sky, these are both different patches taken from the sky, but they're so similar that when you look at the difference between them, you end up with something that's pretty close to zero once you square the whole thing. Once we go up to an edge, um, when you move it perpendicular to the edge, you'd see a higher difference than you would see with patches of the sky. but if you move it along the edge, it's still low. So the sum of squared differences is still not good enough. But when we take the case of a corner, no matter which direction you move your patch, once you subtract the region um, from itself, the difference that you see after you square it will be the highest of these three cases. And visually, if you look at a surface plot of intensities around where a corner would be, where an edge would be, and where something that doesn't have a lot of variation would be, um, the region with a corner stands out. So if you had another surface that's kind of like this with the peak in a different spot, you would still be able to line up the two. Well, I call this a peak, but it's a local minimum. Um, this we know what we're looking for now. That begs the question of how do we find this? This group of plots should give you some hint of how we would try to quantify a corner. What is changing here? Who said that? Louder? Right? And how do you find those? Right. So since we can't directly differentiate these, we use some of the discrete derivative operators that we looked at, like the Sobel, Pruitt. That tells us something about um, the gradients around a pixel in a patch. And we have the ability to do that in both directions, x and y. So that might be a step towards an approximation for finding corners. So when it's more or less flat in terms of how much change there is, gradients aren't going to be large in either direction. This is your classic edge detection case. You have your gradient changing once and then coming back down. And when you look at the orientation of the gradient, it will be only in one direction along the entire edge. Still not where we want to be. But if we can find the gradient changing twice and two directions, then odds are that's a corner. So we want gradients within a patch, and each patch is centered on around a pixel. And we need gradients in the entire neighborhood. The way to do that is by calculating what's called a structure tensor first. It looks a bit scary, looks scary to me at least. It's really not. So uh, the I, X, and IY terms are gradients, and P and R refer to centers of patches. So you have two patches that you're subtracting the gradients of along the X direction, along the Y direction, and your W is a weight. So we apply smoothing to the gradients that we get. W would be just a Gaussian filter that you multiply with each term. So we do this for every pixel in the patch. We first use the Sobel operator to get the gradients along X and Y, which is your IX and IY terms. Then we create a Gaussian weight matrix, which is just your regular blurred circle within a grid. We pick whatever standard deviation we want, depending on how much so a higher standard deviation means that pixels that are farther away from the center within the window will contribute a bit more than if you have a lower standard deviation value, where it just wouldn't prioritize pixels far from the center as much. And then we compute each of those terms in the structure tensor. So we have an IXX, IYY, IXY, and we multiply a weight with each of those terms, where IX is the product of the derivative along X, IY is IYY, it's the weight multiplied by product of the Y terms, and there's the XY term. And then we sum all of these over the entire patch, because we're doing this for each pixel within the patch. And then that gives us these values. So in summary, we calculate the sum of gradients along both X and Y within a patch for each pixel, and multiplied by a Gaussian filter. So that gives us some idea of what the gradients are like around each pixel, but that's still not enough. We need to be able to, how do we go from there to corners? And that's not something that I'm gonna ask you to guess. We calculate the eigenvalues for that particular structure tensor. The eigenvalues describe the magnitude and intensity of changes along principal directions. So these are magnitude and intensity of changes along X and Y, basically. And the eigenvectors, sorry, the principal directions are what you would get by doing the eigenvector eigenvalue decomposition, and the direction along which you have the maximum amount of variation is your principal direction, and eigenvalues describe the magnitude and intensity. The videos that I've linked go into it in a fair bit of detail, which is beyond the scope of the class, really. But if you're curious about the math, you may look into it. So we know about the gradients around pixels in a patch. We want to find out eigenvalues to see how big the changes are. And we do that by solving for lambda, which is the eigenvalues. So we take the determinant of this particular matrix, and that's this term times this term minus the product of these two. So you end up with an S square XY here. And you have these two terms multiplied as your first term. Expanding that, you get the same thing rewritten, and then we can apply a quadratic formula to that, which will give us two lambda values, which is our two eigenvalues. When the two eigenvalues are both small, then that means there's hardly any change. When one of them is much larger than the other one, that means we have a gradient, but it's going only in one direction. So what we need is for both of those values to be large and similar. There's a neat function that wraps all of that logic together. It's the Harris corner response function. And the way you do that is by taking the determinant of the structure tensor and subtracting an empirically chosen k times the trace. And trace is defined as the sum of both eigenvalues, and the determinant term is the product of both of the eigenvalues. And when you compute that, so for this particular image, the corner response looks like this. And then we threshold that, which gives us this. And then similar to how we did it for the canny edge detection pipeline, we apply non-maximum suppression, which leaves us with just whatever the maximum corner response in a particular region is. Are you guys able to see the little red crosses on there? Those are the corners that we get by applying the Harris corner detector. I should put that in here. Okay. So from the top, we start by computing image gradients using the Sobel operator or any other filter that gives you the discrete derivative. Then we compute the products of gradients at each pixel, which is our Ix, Iy terms. And then we apply a Gaussian filter, which is the weighting step, to give us the S terms for the structure matrix tensor. And then we compute the Harris response, which gives us what the implicit eigenvalues are. And then we threshold it, apply non-maximum suppression, and that gives us a whole bunch of features. So this particular example, there's more features. Corners is just one. I'll be talking about scale and rotation invariant features next class, and how to stitch them. So this is an involved process. The end result, once you're able to find all the features and match them, would look something like that for this particular example. So we motivated the need for features through the panorama stitching example. Some other things that you could do if you have features. Has anyone heard of SLAM? It's a robotics thing. So when you have robots that are in, say, maybe they're indoors. If you've ever been to like a sushi place that has one of those robots that bring it, they need a way to navigate indoors where you can't use GPS and it's too constrained of an environment. So they do it similar to how we do it visually. And you do that by finding features in your environment and using that to build a map of the world around you as you traverse it. So that the simultaneous localization and mapping is you're mapping the environment while you're also locating yourself within the map you're creating. These two images, at first glance, does it look like they come from the same region? it's really hard to say whether they're from the same place or not, but when you extract features from it, there's a whole bunch over there, and the distribution of features is similar to what's over here. So we're able to say that this uh, image comes is a different perspective of this region over here. We're also able to search for objects. We have a candidate region that we want to find, and this set of features over here corresponds really nicely to this set of features over here. So we know that this, in a different perspective, is present within this image. We have corners now, but there's a lot of corners. Um, how do we decide which ones match with which other one? For each corner, um, in addition to, so since the way we do this is by evaluating patches of images to see if they contain a corner, for every maximum in the feature map that we have after non-maximum suppression, we know that that response came from a region around it. So we have that entire patch that we looked at. We can compare patches by calculating the sum of squared differences, but comparing every patch with every other patch, same problem, a lot of computation. There's another problem. So we do have patches, but if we try to compare pixel values directly, is that really good enough? Anyone have any thoughts of what case this would fail in if we're comparing patches of pixels directly? Okay, that's fair. Assume the intensity values are the same. So think of the template matching example from last class. What would happen if I rotated the image within which I'm looking for my template? I'm never going to find it, since that's what happens to a patch also, along with the actual image once it's rotated. Oh, this box should not have rotated with that, but assume that the box is, the box didn't change, but the image rotated. So the values of pixels that you have within the patch, even though like once you rotate them back to the original position, they'll have the exact same values. But when you subtract it the way it is right now, there's going to be a pretty big difference, because this region's dark, this region's bright, and the opposite's going on over here. This part's dark, that part's bright. You'll see a positive difference in one of these and a negative in the others. And once you square it, it's a pretty huge difference. So pixel patches, not good enough. We need a good way to represent feature regions, and we also need to be able to transform the images once we identify what the difference between the two halves of the image that we're trying to stitch are. So I'll be going over that next class, which is how to represent feature regions and how to identify pairs that match. We'll be talking about an algorithm called RANSAC, which is random sampling and consensus. Speeds up the whole process so that we don't have to do however many corners squared. number of computations, and we'll also expand on the transforms that we looked at earlier to add in prospective transforms, because that's really the only sort of transform we haven't dealt with yet. And doing that in this context would help really cement it. So I figured I'd go over how to set up the homework and interact with the environment. Um, is there any part of what I covered just now that anyone wants me to go over? Any questions? Okay, so just quick show of hands. What is everyone using? Is everyone on Windows? Hands for Windows? Okay. Uh, hands for, oh, okay, I see a couple of MacBooks over there. Okay, it looks like an even split. Is anyone on Linux? Ooh, okay, all right. Um, so to start off, how about, I'll do Windows first. Um, First thing that we want is, okay, I'll just do it the way you guys would. So we go to the assignment, look at the PDF. That's not assignment. So where we go? There we go. Okay, so everyone's been able to uh, get their accounts linked to the GitHub Classroom, I hope. Anyone have any trouble with this? I'll take that as a no. Uh, Now, going to the actual repository itself. um, So this is my version of the repository, which gets cloned to all of your accounts once you accept the assignment. Um, First thing we need to do is to get this code onto our computer. So there's a couple of ways to do that on Windows. There's either GitHub Desktop or the command line interface. So I'm going to do it with the CLI. We go to the CLI website, download that. So that's installed. Now to see if it's, actually I should just mirror this from. Okay, yeah, this should be better. So I have it downloaded. I installed it. Now I need to see if it's a recognized command or not. So typing GH should print out a bunch of GitHub related stuff. And this will be more or less the same regardless of what you're trying to install it on. So for OS X, I believe you'd be doing, if you already have Homebrew installed, I believe that should be the way to do it. Yeah, so you have your homebrew command, brew install gh, which bypasses the whole downloading and installer part, setting it up. Similar for Ubuntu also, you would, there should be I know that it comes bundled with the Ubuntu package manager. I'll get to that in a second. So we now have the GitHub CLI. We copy the GitHub CLI command and just pick whatever directory you want to use. ls lets you list whatever is in there. You can create a new folder if you want. That is done using the make directory command, which is mkdir. And I'll call this test repo. So it created that folder for me. To navigate into it, I will do cd, which is change directory, and hitting tab usually completes a lot of file paths and stuff for you. So if I just press that much, hit tab, it gave me the whole thing. I'm in that particular folder now, which is where I want this code to be. So I copy the command, paste it in here, and run it. Oh, okay, so Git is not bundled with that. We need to install Git separately. Git is the tool that the GitHub CLI is built on. So this is what your actual version control is, and this is what you'll be using for committing your code when you're done implementing a part. So we install that with all the defaults. Here, instead of Vim, I'm going to choose Visual Studio Code since I have that installed and I like it. Let Git decide. Keep all the recommended settings. Okay. And once that's installed, I'm going to test it. So I open up my terminal again, just type in git, and it's a recognized command now, so that's good. Pressing up arrow will take you to whatever command you ran earlier. So I have this command that I pasted before, but I still need to go into the directory that I created. Forgot what I called it. Test repo. Yeah, okay. And we clone our code in here. Since I already had this installed before I uninstalled it to demo this now, it didn't ask me for anything, but when you run it the first time, you'll have to log in. So it will spit out an error that asks you to run the login command, and that's what the command is. So when you press enter there, it will give you two choices. You pick github.com, pick HTTPS. Authenticate with your GitHub credentials is what we want to be doing. So we log in to a browser, but first copy the code. And when you press enter, it should open a new tab like this. Paste the code in there, continue, and authorize. I already have it authorized, so I'm not going to do this. I have two-factor set up for my account. But once this is done, you would then go back and run the clone command. And after that, you'll have the code downloaded, which you can check. So you go to your file explorer, and I forget where it was. I think it should be, whatever the path is over here is what we want to check. So I have to go to see users, Varun. Um, and in here, there should be test repo, and I have the homework now on my computer. So that takes care of how to get the homework here. Next is we need to be able to run the code, which is a Jupyter notebook. So on Windows, it's a bit easier to deal with that when you're using Anaconda. So um, on Ubuntu and OS X, I find it easier to not have the whole user interface that Anaconda does. So you just skip registration over here, get the Windows one. I already have that downloaded, I think. So I'm not going to download it again. Yeah. Uh, you wouldn't have to do all of this on a fresh install. It's only because I had this installed earlier. Anaconda 3, I'll just and pick all the defaults, install it. In the meantime, VS Code is something I like. Um, the you're free to use it. The only exception is that you're obviously not supposed to be using something like GitHub Copilot, which is LLM-backed code completion. Regular whatever's built in is fine, but you want to be doing the code yourself so you understand what you're doing. And the thing with using LLM powered code completion is that it spits out code that looks pretty good a lot of the times, but it won't do what you intended to do. And debugging is harder than writing code yourself. So just you'll end up wasting a lot of time. Plus, if your code looks too good, and if I catch you, then you're going to be in trouble. Which isn't to say that if you know how to do that stuff, you shouldn't, but just putting that out there. VS Code, pretty straightforward install, just download the exe, install it. I'm not going to do that part, but it ties in very neatly with a lot of the things that we're going to be using. So feel free to use it if you want. Example of why it's cool. I opened my folder. Oh, I already have it open. There's a built-in terminal. So you can do all the PowerShell stuff in here. You can run your notebook in here. So I'll do this later, since it's sort of muddying the waters of what I'm trying to get across. So we have Anaconda installed. And the good thing is the dependencies, which version of Python to use, what version of OpenCV, NumPy to use, you don't have to deal with any of that. I already set up an environment. So this is what you'll be greeted with when you first fire it up. It does this a lot. We want to go to environments and import the one that I've shared with you as part of the GitHub repository. So we find that directory, go in there, and it's a .yml file, and open that. I think yeah, once you get the option to import it, and this will take a while. So I'm gonna wait for that oh, that was quick. I guess I already had all the packages cached. Oh, wonder what happened there. So in a case like this, where I think something broke in my computer, because this is not the computer that I made the environment on. I first, what's good to have is your Conda integrated with a terminal. So if you try this in here directly, I don't think that works. Yeah, this is why I recommend using Anaconda on Windows, so that you have the PowerShell prompt that you can launch from here. This is something that you want to check every time you're trying to run something. So if base shows up, then you're in the default Conda environment. And we need to run our code from within a different environment that has all of the packages that we need. So first, I have to go back to the directory that I made that contains the YAML. And here the command is conda and create. Give it a name with the N flag, and a file with C573 YML. Oh. Okay. It's the same thing that runs under the hood when you do the GUI-based import. Only thing is that here, if something breaks or if you have a version mismatch, you get to see that. So if you run into problems and want to ask me on Piazza, then output from doing it in the terminal would help identify what the problem is. A bit temperamental. It takes some trial and error every time you want to set it up on a new computer, or for a new project that has a certain version of something that's required, which is why being able to export the environment directly is useful. The other alternative way that I could think of packaging everything for you guys is to make a Docker container, but I felt like this would be more useful in the industry, just being able to deal with these sort of issues on your own. So once it's done finding versions of everything that play nice with each other, it will, yeah, so it looks like that worked. And when it works, it will say that it was installed, and to activate it, use that command. So every time we want to run our code going forward, that's the only thing that we'll be doing, which is, where did it go? The PowerShell. Oh, right. So the PowerShell prompt that I had was installed on my base environment, and it's not part of the environment that I shared with all of you, because this package wouldn't work if I had included it, and you tried to install that on Ubuntu or OS X, it would error out. So this is an additional step if you're working on Windows and want to use the terminal. And looks like that's installed, so I'm going to go ahead and launch it. Where are we? Oh, right, things that are installed show up close to the top. And go back into the directory. Now, oh, right. So ls, just to check that everything's here. And then if I say Jupyter Lab, that should open up and then a window that looks like this in the browser. And you also see your files in the directory over there. Double click homework one, and that gives you this notebook. The way to run this is you go on each cell and run the cell in advance. The shortcut for that is Shift Enter, so I'll be using that going forward. So you have to run every cell in sequence if you want to be able to. So over here, there's this function call that runs the function main, which is defined in this cell, but it also makes references to these functions, load image, grayscale, invert, which are defined up here, but I haven't run these yet. So far, the only thing that the interpreter knows about is the load image function. And what's going to happen when I run this is that the image will get loaded, but that's it. It's going to error out after you get to grayscale. So it says grayscale is not defined. I can go back up to the grayscale function, run that cell, come back here, and now it breaks at the next one because it knows what the grayscale function does, even though it's not doing what we need it to be doing. So in your code, you will only be changing logic within here. So to grayscale an image, you'll replace this line with some logic that does something like image plus whatever. Whatever your operations are in here, I'm not gonna do what the actual thing is, obviously. And then that value gets returned by the function call. So the only things you'll be changing in this homework are the definitions from there to here. These cells. And then, assuming you had all of these outputs, then running the final one will print out, will display the image that you want to see. So that is how to set it up and interact with the homework on Windows. Um, I mentioned VS Code earlier, so you can have everything in one place pretty neatly. If and this also lets you bypass the conda activate and Jupyter Lab commands in PowerShell. If you just open up the folder, double click that, and go on the first cell, shift enter, it will ask you to choose from an existing environment. So just pick the one that we created now, and it will, you use it pretty much the exact same way in here. And that's another way to deal with it. So the next part is committing after. So after you implement every function, I'm just going to change this to return the actual image itself, or maybe I'll average the 3 channels. That's not the actually I'll max, and this is I'll do it along the last dimension, print image dimensions. So when I run this, even though it's not doing what is expected. Oh, if you want to just test out a single function, where did mine go? You can add cells below by just pressing B when you're not inside, but when you're selected that cell. And I think I already have image loaded. No, I don't. So image equals load image, and you supply the path to the one that image.jpg. Once that's loaded, I'm getting those completions because I use Copilot. You can't. Yeah. So this is not the right logic, because I'm checking the maximum, and that's not what you're supposed to be doing. You're supposed to use the formula that's in there and apply the coefficient to each channel. So you're able to look at individual function outputs like that. And yeah, once you're done, this whatever logic you have in each, all of those functions together, actually, I think you should be able to run the final one, even if you have everything. Oh, it's because I'm not saving any images over here that, yeah. So I commented all of those lines out. And yeah, so your final output will look something like this, a grid of images that have all the transformed variants. Does that leave anything? Oh, committing, right. So once you make changes, first thing to do is obviously save the notebook. Now that it's saved, I'll do it the old-fashioned way, not in VS Code, but it's essentially the same thing wherever you do it. You make sure that you saved your code, and then open another terminal. This one doesn't necessarily have to be in the same Conda environment. Since we're not doing anything Python, that requires dependencies, but we go into the same directory and say git status. And that tells us that homework 1 was modified since we just made changes to it. So um, to see what differences there are, we say git diff. This won't really make a lot of sense for Jupyter notebooks because the way they're represented under the hood is not very readable, but you scroll through it uh, using your arrow keys or page down. In here somewhere, I think we should see code changes. No, these are encoded, never mind. To commit it, once you're able to see that there's something that has changes, you say git add and type in the name of the file that with the changes and say git commit. The M flag is to add a commit message, and I'd say something like, actually, I don't want to make my I created a new branch. You don't have to know how to do all of that. I'm just doing it so that I don't add any gross stuff to my main code. So I'm going to commit the changes I made with a message that describes what the changes are. Uh, mm, so it shows a summary of what changes there were, and then you say git push. First time that you do that, you'll have to set a target place to push your code to. So just this is since I created a new branch called demo, and that doesn't exist on the GitHub server. So you're probably not going to see that. And yeah, now if I look at Git status, branch is up to date. There's no changes, nothing to commit. Everything's good. So this sequence of git status followed by git add whatever files that have changes, followed by git commit with a message, and git push. Those are the four commands that we'll be using the most. And that is how you get your code submitted. Whatever the last commit is before the deadline is what I will be grading. So yeah, that I think covers the entire workflow. Is there any part that wasn't clear in terms of, yeah? Um, that, so let's see. If I read an image in, it's just the way OpenCV reads images. It's documented, which is why that's the standard way it's done. But let's call this BGR image. So I look at BGR image dimensions. It's a 784 by 640 height, width, and number of channels. Now this could be anything. Default usually is RGB. So assuming that this is also RGB, if I tried to display it, then uh, I'd get the wrong image. So this should be like brown, pink rather than blue, which is why there's that color space conversion. Because OpenCV reads images into BGR by default instead of RGB like every other library does. The same thing if you try to, do I have this imported? No. There's other ways of loading images. This is another one. If I image open, what is it? Now this one, if I try to display it directly, it's going to show up the right way because I use Pillow instead of OpenCV to load the image. And the way Pillow does it is it loads it into RGB by default. So it's just a like compatibility thing between libraries. For the image, this I think should have some sort of metadata. Um, it depends on at what point you want to know what format it's in. So the thing is, with OpenCV, all of the whatever transforms accept color images, those typically expect BGR because that's just how OpenCV is written. So color wherever usually by default it expects BGR. But if you want to deal with it directly in NumPy or use say scikit image, um, then you'll have to do that conversion. And to check within the image itself, if you look at the raw values, there's nothing in there that would tell you that it's BGR. When the file is saved as a JPEG, there should be metadata for it. And when that image is loaded up, the convention is RGB. So that's just how it's displayed if you open it directly in your operating system. Image, I wonder what the, so if you look at the documentation for the image module and see what attributes it has, image shops, image color, get color. No, I don't think that's it. Maybe it's an attribute for the image file. I'm not sure. You could probably also use like some library that lets you interact with the file system directly to get whatever metadata the file has. There's different levels at which you can access it. I'm not particularly sure how I would do that in here. It might be, oh, so EXIF tags is usually what GPS data is stored in images. There's got to be something like that for color space also. That covers how to deal with images in here. Any other questions? Okay. Yeah, so that covers what I had planned for today. Now, if someone wants to see how to set this up on Ubuntu, I can try to do that also now. It just means that you're going to have to stay a bit later along with me. If not, then your call. Yeah.
Card, is it okay if we write handwritten it and scan it?
Yeah, that's fine. Anything works. Ideally, formatted in LaTeX. A little less readable would be if it's in Word, but those take time, I know. So written or iPad is fine. Also, oh, I almost forgot. A couple of people left. I'll post this again on Piazza, but I want you all to start thinking about what you would build for a project. I'll be putting out an assignment of sorts that asks you to come up with a proposal for a project. So if you intend to team up, at least start thinking about that now. I'll put out a Google form for whoever wants to form teams. And yeah, probably next week I'll put out the request or rather assignment for a proposal. And the week after that, you give me your proposal for a project. Um, Another rule of thumb, try to pick something that you would be able to implement either on your own computer or using Colab's free tier GPUs. Um, if you do have your heart set on something that's very complex and requires GPU access, I was able to talk to the people at CCR. They're willing to give us an allocation. Um, what I don't want is for us to be bothering them with issues. If you do end up going that route, there's things to know like GPUs are in demand. It takes a while to get a GPU allocated to your job, sometimes even up to a day. So we can't keep reaching out to them saying, hey, I don't have a GPU yet. Um, yeah, so if your project does end up being something that complicated that you can't run it on your computer or on Colab, then let me know and I'll get you CCR. Yeah, that was it.
Regarding the code pushing onto the GitHub,
Mm.
it says like only one attempt to push, it will get 0 points or something like that.
Yeah, so what I said in the document is that you need to be making commits after you implement every function, which is every subtask. But if instead I see there's just one commit and all the logic was implemented and pushed within a single commit, that you went from 0 to complete in one commit, then that's not acceptable.
But the thing is, there are functions, right,
Yeah.
which will be run at the end. Like unless and until we write the logic for each and every function, run it, we work with it.
No, I mean, I showed you how you can test individual functions, right?
So can we do that?
Yeah, yeah. The objective is not for me to see the entire output, um, but just that there's a log of when you did what.
The written part is gonna for latex.
It's not a requirement, no. If you do it in LaTeX, then yeah, I'd love that, but I know it's overhead and there's what, 4 days to go, 3.5. Um, if you I wouldn't prioritize that. You're not going to lose points if you don't use LaTeX.
For the rotation task,
Yeah,
it says you have to implement the rotation matrix.
yeah.
Do you want the matrix or can just implement it as algebraic function?
Uh, it should be, so you have pixel coordinates in your original image. You apply the matrix to a pixel, find what its new coordinates are, copy over the old values. Um, so you will be using the rotation operator matrix.
Do you want the operator for every task?
Uh,
So currently what I'm doing is I'm just finding the new coordinates using algebraic. Let's say I'm just flipping, I just do minus.
For flipping, yeah, that would be fine. rotation,
Rotation, it was mentioned explicitly that you need a,
yeah,
that we need to perform a math.
yeah, for flipping, that part's fine. Just don't tell the logic out loud like that. Uh, yeah, that part's fine. I mean, as long as your output looks like it should, and you're not using any functions that do it for you, then it should be acceptable.
Something to that instruction.
Shreya, yeah,
So I missed the last.
okay.
So initially I attended the 2 classes and then I thought
Don't worry about the attendance. I know that you registered for the class late, so I'll take that into account.
So, regarding that push, what I've done is I didn't see that instruction and I've committed in a single push. So now what I will do is like I will change the code for everything. And I
You
will
finished the whole thing already? Don't do anything now then. I'll look at it. Just keep it in mind for all
there is-
homeworks
there
going
are some
forward.
corrections, but this is not a final one. Just I tried something, it worked, but I need to do some changes for some functions as well.
Okay, yeah.
So I will do remaining changes and I'll push again. Is that okay?
Yeah, I mean, whether it's okay or not will depend on what your first commit looks like. I'm obviously going to look at your code. If something feels off, then I'll talk to you about it. If not, then it, it's fine. Just for assignments going forward, just keep that in mind. Commit whenever you finish one atomic unit of the problem statement.
Just want to talk regarding my friend.
Yeah.
Actually, for this course, he also reached for all course as well, and he dropped the summer course because he due to some family emergency, he had to flew back to India. But what happened is due to some technical issue, this course like, it's still there. They didn't drop.
So you should talk to the department
Yeah,
for
we
that.
talked to the department and they said there's nothing we can do. And he finished with the emergency and he's coming back with the to attend the classes. He'll start attending the classes from next week.
Okay.
Just he missed this 2 3 weeks classes. And he'll be attending from classes from 18.
Okay, so what do you want me
So
to
I just want to
do?
inform like the 6 days courses and any quizzes in the next class. Like, is there any possibility he can do one?
Ask him to send me an email just so that I have the whole thing in writing. Between now and the class next week, there's going to be at most one quiz, and there's a total of 5 quizzes, of which I'm considering 4. So even if he misses that one, he should be fine. Attendance, I'll consider whatever his situation is. Homework, I'll- I mean, if he is in a mental state that lets him do that, then that's fine. If not, then I can give an extension. I'll talk to him directly about that. Okay.
Thanks.
Yeah.
Thanks, sir.